Alternating series are unique, but they're usually pretty easy to identify because they alternate in sign. We're talking about going from a positive term to a negative term, positive term, negative term. So an example of a series that did that would be 1 minus 1/2 plus 1/3 minus 1/4, etc. So that in sigma notation would be n equals 1. We're dealing with an infinite sum here. We would use -1 raised to the n plus 1 power. And then, of course, we could multiply that by 1 over n. Now, that is the same as just putting that -1 to the n plus 1 power in the numerator. So you would see that quite a bit, but when you plug that 1 in, whenever you have a positive exponent, you're going to get a positive answer. So we're going to have a positive, and then that's going to automatically alternate to negative because this is a -1 raised to that power. So that's going to be pretty easy to identify. There are some unique situations that might make it a little bit more challenging, but anytime you see that -1 raised to a power, you should be able to recognize that it's alternating. Now you also could have something along these lines where you've got the factorial. Now that is still alternating. So we would write that as -1 to the n power over n factorial. And the reason why we don't have the n plus 1 is because that first term is negative. It's important to recognize if the first term is negative or positive. Obviously, if you plug a 1 in here, you're going to get a negative. Just because you see a -1 raised to a power, though, doesn't automatically make it alternate. I know I said that was a big indicator, but you do need to be careful. So these are situations, let me get a different color here. These are situations that are not alternating. And it's going to make sense here. But if you see that sigma notation, and you've got the -1, but perhaps it's raised to the 2n power. That's always going to be an even exponent. And if that's an even exponent, this is not going to be alternating in sign. Same thing happens with a situation like this, where you've got the sigma notation, and then maybe -1 raised to the 2n minus 1 power, because this is the same as just factoring out a negative, because you're always going to get a negative exponent out of this. So you could actually just factor out a negative and raise this, I know I'm running out of room here, and raise this -1 to the n. So that would be the same thing. So just interesting to recognize. Obviously, the -1 is a huge indicator, but if you have that positive coefficient here, or even coefficient, I should say, you're just going to have to be careful about it. In general, just knowing that the limit is equal to 0 doesn't tell us a lot. If the limit is equal to 0, remember, that doesn't necessarily confirm convergence for us. If it's not equal to 0, that does fall under the nth term test. That would fall under diverging. But just because it's equal to 0 doesn't necessarily mean it converges. However, with alternating series, it kind of does. And we'll talk more about that in a bit, but we have 3 conditions. So when you've got an alternating situation, we call this the alternating series test. It is called the Leibniz test as well. But you've got the limit as n goes to infinity of a sub n, as long as that is equal to 0. And this is what you would see in a textbook. If you've got a sub n plus 1 is less than a sub n for all n. So what this really means is that you're dealing with a decreasing function. So the conditions for us would be listed as alternating in sign. That's the first step. Alternating signs, decreasing in magnitude. Okay, decreasing in magnitude. Technically, this should have absolute value signs around it in order to indicate the magnitude piece. And then the last condition means that we have a limit as a sub n oh, excuse me, as n approaches infinity, excuse me, as n approaches infinity equal to 0. So those are your 3 conditions for an alternating series to converge. Now, I will say that you have to be very careful. The alternating series gets a little quirky at times, but we do use it quite a bit. The alternating series test can only prove convergence. It does not guarantee divergence. If you were to use these conditions and found out that we didn't decrease in magnitude, i.e. the limit as n approaches infinity does not equal 0, you don't diverge by alternating series test. You diverge by nth term test. That's a test we've already used. We already are familiar with that. So you can never use an alternating series test for divergence, right? You have to use an alternating series test to prove convergence. So let's look at what this first example is. Determine if the following series converges or diverges. When I see that -1, I'm going to take a look. We're going to build the first few terms of the series so you can see what this is. If you're not in that habit, that may be helpful to you, especially with some of these that are more complex. So I'm going to take this in, I'm going to plug it in. If I plug in a 1, this is going to be -1 squared. So this is going to be positive. So we're going to have a positive 1 on top. Again, I plug in a 1 down here. I get 2 minus 1. So I'm going to end up with a positive 1. Then the next one, I'm plugging in a 2. So this becomes a -2. And then on the bottom, 2 times 2 minus 1 is 3. So I'm going to go ahead and erase that plus and make it a minus. Minus 2/3. Then the next one, plug in a 3 here. So you can tell kind of the pattern of what this looks like. And I think it's really beneficial for you to build the first 3 to 4 terms so you can tell what's happening. I can see that this alternates. You're going to have to write out your conditions. So we're going to say alternate signs, right? Check. Decreasing magnitude. It's okay to abbreviate. Check. And then we're going to take a look at the limit. So what we're going to do, that wasn't very pretty. What we're going to do is we're going to take the limit as n approaches infinity of both the positive and the negative version. I'm not really worried about this piece. I'm just going to make this as the negative and positive portion. So I'm just going to look at n over 2n minus 1. So we're going to do the positive, and then we're going to do the negative. Negative n over 2n minus 1. So when I look at that, I can see this is spit in the ocean. Those n's reduce. I'm going to get 1/2 here. I could stop there. If the limit as n approaches infinity isn't 0, this diverges because my conditions fail, but it diverges by nth term test. But I am going to go ahead and confirm that the bottom is also -1/2, right? So that doesn't equal 0. That doesn't equal 0. So let's go ahead and make a note here, right? Conditions fail for alternating series. I think you get that. So we're going to say, therefore, series diverges by nth term test, not alternating series test. So alternating series and nth term work really closely together. The next one, I'm going to do the same thing. I'm going to build the first few terms, plugging in a 1 here, so you're going to get a -1 as your first term. Then you plug in a 2, you're going to get a positive 1/4. You plug in a 3, you're going to get a -1/9, right? Then positive 1/16. So I can tell that I'm alternating. I can tell that I'm decreasing in magnitude. So alternating signs. Check. Decreasing in magnitude. Check. Now I want to check the limit. The limit as n goes to infinity. And again, I'm not worried about the whole -1 to the n. It's either going to be a 1 or -1 every time. So that's over n squared. And then, of course, the limit of the negative version is also 0. So because all 3 conditions are met, we're going to say the limit as n goes to infinity of a sub n equals 0, right? All three conditions are met. Therefore, series converges. Now, it converges by alternating series test. You're not required to show the top and bottom, like the positive and negative, both of these limits every single time. I think it's good habit because sometimes we get kind of stuck and forget that we have to consider both. But as long as you claim and check the limit as n goes to infinity of this nth term, then you should be able to establish that condition. And if all three conditions are met, then you can prove your convergence.